Good day everyone. Today we will be discussing on the topic motion. Now to begin we are going to be defining some common terms involved with motion. Now the very first term we are defining is motion itself. Motion is any form of movement, either a circular movement as in the case of the earth in its orbit, straight line motion as in cars moving over a straight short distance, free falling objects or free falling bodies as in the case of falling mango from each tree, etc. The next term we will be defining is speed. It is the rate of change of distance with time. That is, speed is equals to distance over time, and the unit is meter per second. Also, average speed is equal to the total distance travelled or the total distance covered divided by the total time taken. Now the next term we will define is velocity. Velocity is the rate of change or displacement with time. It has the same unit as speed. The only difference between speed and velocity is that velocity is speed in a specified direction. Now the next term we are explaining is uniform velocity. It occurs when displacement is equal to time taken. And there is a direct proportionality between displacement and time. Now for most of our formulas, u represents initial velocity and v represents final velocity. The next term is acceleration. This is the rate of change of velocity with time. That is, acceleration is equal to velocity change divided by time taken. Another term we have is deceleration, also known as retardation. This is also commonly known as negative acceleration. Here velocity decreases at equal rate with time. The final term we are explaining is uniform acceleration. It occurs when the rate of change in velocity with time is constant. For most questions involving velocity, we normally use a velocity time graph. Now the velocity time graph is basically a graph when we plot our velocity against time, and it helps us calculate for or give us an overall idea of our motion. Now some things you have to notice that when the body is accelerating, we represent it as an upward slope, and when it's decelerating or retarding, we represent it as a downward slope. If it's having a constant velocity, it's a straight line, and we normally start our graph from our initial velocity. That is, if the body is starting from zero, it starts from the point where the velocity and the time meet, and if it's starting from a fixed acceleration, maybe 5 meters per second, we are going to be starting from 5 meters per second. Now there are some parameters you can get using this graph. One, apart from giving us the like a broad idea of our motion, we can find our total distance covered, which is the area under the graph. We can also get our total time and other parameters. Now we'll be using these velocity time graphs to solve some questions and explain it further as we get along. We have a question from YA 2010 that states that a car starts from a point A and accelerates uniformly for 5 minutes before it reaches a speed of 27.8 meters per second. It then moves with the same speed for 20 minutes and then retards uniformly for 4 minutes before coming to rest at point B. Use a velocity time graph of the car to calculate the Roman figure 1 distance between A and B, Roman figure 2 the average speed of the car, and Roman figure 3 acceleration and retardation. Now very first step is to sketch our velocity time graph, and since we are starting from zero, we are going to beginning from zero, and since the body is accelerating for 5 minutes, there will be an upward slope that stops at 5 minutes. Then there will be an uniform straight line for the next 20 minutes. Then it's a downward slope for 4 minutes, and sketching all this we get the diagram as shown on the screen. Now the very first part of our question is the distance between A and B, and we know that the distance between A and B is equal to the total area under the graph, which is equal to the area of the trapezium. Now the area of our trapezium, or the area of a trapezium, is 1 over 2 A plus B times h, where A and B are your two lengths and h is the height of the trapezium. Now substituting the value from our graph in this equation, it becomes 0.5 or half in bracket 1200 plus 1740 times 27.8. Now I think it is important to put more more light on how we got 1200 and 1740. Now we converted our time from minutes to second. The total time was 29 minutes, and converting 29 minutes to second to be 29 times 60, which is 1740. Now for our a, that is the top of the trapezium, is between 25 and 5. So subtracting, it will be 20 minutes, and converting 20 minutes to second to be 20 times 60, which is 1200 seconds. Now simplifying this further, it will be equals to 40,866 meter. That's our total distance covered from A to B is 40,866 meter. Now for the second part of our question, the average speed of the car, this will be equal to the total distance traveled divided by the time taken. Now our total distance traveled is 4,866 meter, and our total time, which is 29 minutes, when converted to second, is 1740 seconds. So this will be equal to 40,866 divided by 1740, which is equals to 23.49 meter per second. Now for the final part of our question, the acceleration and retardation. Now we know acceleration is equals to velocity over time when the body is accelerating. So our maximum velocity the body got to was 27.8 meter per second. Dividing by our time, and as usual we are converting from minutes to seconds, it becomes 27.8 divided by 5 times 60, which should be equal to 0.09 meter per second square. Similarly for our retardation, it will be equal to velocity over time, which should be equal to 27.8 divided by 4 times 60, because it retarded to stop in 4 minutes, which will be equal to 0.12 meter per second square. We have another question that states that a body moving at 20 meters per second accelerates uniformly at 2.5 meters per second square for 4 seconds. It continues the journey at this speed for 8 seconds before coming to rest 3 seconds with a uniform retardation. If the ratio of acceleration to retardation is 3:4, Roman figure 1, sketch the velocity time graph of the journey. Roman figure 2, find t, and Roman figure 3, find the total distance of the journey. Now our very first step is to sketch our curve or our graph, and when we do that, we get the diagram as shown on the screen. Now for the second part of our question, finding t, we will be considering the latter part of our sketch, that is the part that concerns retardation. So concerning that part, retardation will be equal to 20 divided by t minus 12, because the entire journey was 3 seconds and the first 2 parts of the journey took 12 seconds. So for the retardation phase, it will be t minus 12. Also, retardation can be gotten from the ratio of acceleration to retardation, which is 3:4. Using that ratio, acceleration divided by retardation is equal to 3 divided by 4, and we know acceleration is equal to 2.5. So therefore 2.5 divided by retardation will be equal to 3 divided by 4. Cross multiplying, retardation will be equal to 2.5 times 4 divided by 3, which is equal to 3.33 meter per second square. So substituting 3.33 meter per second square for retardation in the equation that states that retardation is equal to 20 divided by t minus 12, it becomes 3.33 is equal to 20 divided by t minus 12. Cross multiplying, it becomes 3.33 in bracket t minus 12 is equals to 20, and also making t the solid formula and opening our bracket, t will be equals to 20 plus 39.96 divided by 3.33 rather, which is equals to 18.01, approximately 18. For the final part of our question, the total distance of the journey is equal to the total area under the curve, which should be equal to the area of the trapezium. Now for the up of our trapezium, it will be equals to 12 minus 4, which is 8, and from the bottom of our trapezium, equal to our total time, which is 18. So substituting these values into the area for a trapezium, which is half a plus b in bracket times h, we get half in bracket 18 plus 8 times our maximum velocity, which is 20. So simplifying this to be equals to 260 meter. We have a question from NECO, that's 2004. It is 2 questions in 1. It says that study the above graph relating velocity to time and use it to answer questions 46 and 47. Now for question 46, it says find the total distance traveled in kilometer. Now the very first thing we are going to do is convert our time from minutes to hours. So basically all our time will be divided by 60 to convert it to hours. So if it's 5 minutes, it will be 5 over 60 for hour. Now the total distance traveled is equal to the area of the trapezium. Now area of the trapezium says that half a plus b times a. We know our a should be 30. Our a will be equals to 10 minus 5, which is 5 minutes, but we are converting to hours, it will be 5 over 60. And our b will be 15 minutes, converting to hours, it will be 15 over 60. So in putting this into our formula, it will be equals to half in bracket 5 over 60 plus 15 over 60 times 30. And when we simplify this, it will be equals to 5 kilometers. Now question 47 states that find the acceleration in meter per second. Now acceleration will be equal to velocity over time. That is the velocity during the acceleration phase over time. So it will be equals to 30 divided by 5, which is 6 kilometers per hour. 30 minus 0 is 30 and 5 minus 0 is also 5. Now converting this to meter per second square. Now to convert from kilometer per hour to meter per second square, we multiply by 1000 divided by 3600. So 6 times 1000 divided by 3600 is equals to 1.67 meter per second square. Here are some exercises for you to try your hands on at home. And for more insight on this topic, you can check out our Hidden Facts Further Mathematics textbook. You can get the hard copy in bookshops, or if you are interested in the soft copy, you can get it at the website on the bottom of your screen. Thank you.